This is lesson 210 on compositions of functions. Now, when we talk about composite functions, a composite function is whenever we have a function inside of a function. Now, I'll just go ahead and warn you, I'm going to try very hard to avoid any yo-dog jokes in this video, but I cannot promise that I will succeed in that. So we do have a function inside of a function. So when we talk about the composition of f with g, we've got two different ways of denoting it. We have it using parentheses, is one way we denote it. Also using an open circle, that's another way that we denote it. I will generally use the first of these two notations, so using just parentheses. However, the second form is pretty common, so if you encounter it, if I use it, don't be surprised. It's frequently used, and it's sometimes easier to use that notation, particularly when we have lengthy compositions. So here we're going to focus only on compositions of two functions, but we can talk about compositions of 3, 4, n, as many functions as we need. Now, since we are looking at just compositions of two functions, it's a little bit easier to see what's going on. The overall story is very similar when you increase the number of functions, but it's just less complicated this way. So when we look at the composition f of g of x, what we're going to do is we're going to look at the outside function. So in this case, f. In that function f, everywhere that we see our variable, we are going to replace it with an exact copy of the inside function, g in this case. So for example, suppose we have two functions, f is x squared plus 3x, and g is x plus 1. So for f of g of x, I'm going to take my outside function f, and everywhere I see an x, I'm going to replace it with a copy of g, so x plus 1. So notice that's what we've done here. I've taken my function x squared plus 3x. Everywhere I saw an x, I've replaced it with x plus 1. So my new composite function is x squared plus 5x plus 4. Similarly, g of f of x. We can talk about the composition either way, f of g or g of f. For g of f of x, I've taken my outside function g, x plus 1, and everywhere there is an x, I've replaced it with a copy of f, x squared plus 3x. So in this case, the composite function is going to be x squared plus 3x plus 1. Okay, so here's a simple example of a type of drill problem that we will encounter. So find f of g of 2, where f of x equals x squared plus 1, and g of x equals 5 minus x. For these problems, all we do is work our way from the inside out. So start your way at the very inside, work your way out. So g of 2, that's the first thing we need to find. So remembering our function notation, what this means is I'm going to take the function that we're calling g, and everywhere there's an x, I'm going to put 2 instead. So g of 2 is just 5 minus 2, so 3. But I'm not asked to find g of 2, I want to find f of g of 2. Well, I know g of 2 is 3, so I'm going to stick this 3 inside the next function, so f. I want to find f of 3. So once again, what this means is I take my function f, everywhere there's an x, I'm going to stick in a 3 instead. So this becomes 3 squared plus 1. So that's 9 plus 1, so 10. Simple as that. Now what if we turn it around? What if we had instead asked, what is g of f of 2? Well, you might think, well, it's the same thing, it's just changing the order, so it's going to be 10. That, unfortunately, is not true. F of g of 2 and g of f of 2, when we change the order, they're not necessarily the same thing. So let's take a look here. Let's do the same process, work from the inside out. So first we want to find f of 2. That will be 2 squared plus 1. So in this case, 5. So now I plug this back into the outside function, so g of 5. So that's going to be 5 minus 5, so 0. So the order does matter. F of g of 2 is different from g of f of 2. Now, For this problem, this has nothing to do with the instructions. I just wanted to demonstrate this. So for our drill problems, this is the answer. We're done. These are meant to be very quick problems so long as you understand what to do. We're always going to have fairly straightforward functions. We're always going to have, well, generally going to have nice values working that work out here. It's just a matter of plugging in this number into the inside function and then taking that resulting number and plugging it into the outside function. It's always going to be a simple two-step process. So here's another one. So we want to find f of g of negative 3, where f is the absolute value of 3x minus 5 and g is 2 minus x squared. So we just work from the inside out. First I want to find what g of negative 3 is. So it's going to be 2 minus negative 3 squared. That is a square. There we go. So that's going to equal, so this is 2 minus 9, negative 7. So now I'm going to take this number and plug it into my f function. So I need to find what is f of negative 7. So that's going to be the absolute value of 3 times negative 7 minus 5. So 3 times negative 7, that's negative 21. When I subtract 5 from that, that's going to give me negative 26. But since I'm taking the absolute value of it, my final answer is positive 26. So these will always be simple two-step processes. Plug in this number into the inside function, take that resulting number, plug it into the outside function. So these should be fairly quick and easy problems. Now the application problems are a little bit trickier. I won't say more difficult. They take a little bit more caution, a little bit more work. The application problems, we're going to be looking at finding the domain of a composite function. So here's an example of such an application problem. So we have two functions here. So f of x is 1 over x squared plus 4, and g of x is square root of 2x minus 6. So we're asked to find the domain of the composition f of g of x. So if we look at what the composite function would look like, again, what we do is we take our f function, and everywhere there is an x, I'm going to put an exact copy of my g function. So it would look like this. That x squared, I replace the x with a copy of the square root of 2x minus 6. So my function becomes this. So let's move the 1 over. So my composite function looks like that. If I go ahead and simplify things, and I square a square root, they just cancel each other out. So I will look at this and say, all right, 1 over 2x minus 2. I know that the domain of this function, that bottom can't be 0. So I want to make sure that 2x minus 2 does not equal 0. So that means 2x cannot equal 2, so x cannot equal 1. So you might think, okay, this is my final answer. My domain is everything except 1. That would be correct if we were asked to find the domain of 1 over 2x minus 2. However, we were asked to find the domain of this function as a composition. So there's one more step we need to do. We can't get to the outside function if we don't get through the inside function first. So in addition to looking at the domain of the composition itself, we also need to look at the domain of the inside function. So our inside function, remember, that's going to be square root of 2x minus 6. I know that that needs to be bigger than or equal to 0. So 2x needs to be bigger than or equal to 6. X needs to be bigger than or equal to 3. Okay, so I need to satisfy both of these things. X needs to be bigger than 3, and x needs to not equal 1. So if you're not sure, you can draw a number line. So x not equal to 1. So here's 1. Let me put an open circle there. X is bigger than or equal to 3. So I'll put a filled in dot here and shade to the right. So the region that satisfies both of these things is just this part right here. So my final answer here is going to be everything between 3 and infinity. That's a 3, not a 5. So we have to check both things. We need to check the domain of the composition. What does it look like when we put everything together? And the domain of the inside function. You have to satisfy both of those when finding the domain of a composite function.